Hello guys, welcome to this lecture. This is not rather a lecture but a simple talk, a general talk on adiabatic process. And in this video I shall explain to you from the Feynman's book, Feynman's lecture on physics, that what is adiabatic process and what is the mechanism we can use to contemplate the ideas that are certainly involved in this process. So we shall talk about that. So first let us talk about the force, the work done and all that thing. So let's begin. So imagine that there is a container, okay, and that container has a piston on it. That's a container and that's the piston, okay, and this container has gaseous molecules doing random motion, okay. Now first we all have that idea that force is defined as pressure into area, okay. I think that this equation is omniscient, that is known, this equation is known to all. But what else we can think about force? So imagine that this area is vacuum. If this area behind piston is vacuum, then with every collision the molecules will make to this piston, the piston will accelerate, okay. This piston will gain momentum, and we can say that the rate at which the piston picks up speed, or let's say it accelerates, is proportional to the force on it, okay. We can say that the rate by which the piston accelerates is actually proportional to the force on it. So we see that the force, which we have already said as force equals to pressure into area, is equals to the momentum per second that is being delivered to the piston by colliding molecules. So we have that idea that force is actually, I'm writing it just because we already, but to have something written I'm just writing it. So the force is actually the momentum piston gains per second by colliding molecules, okay. That's the very notion of force. So let me repeat it once, that if force can also be expressed as pressure times area, but it is actually from the very idea that it is actually equal to the momentum per second delivered to the piston by colliding molecules. That is, I think, very obvious. So I'm rubbing it just to make more space, which shall be used later, okay. Now let us imagine that how shall we calculate the force, okay. So to calculate the force we need to calculate the momentum, okay, and we need to calculate the momentum by every colliding particle on the piston. So we'll do this job in two parts. In first part we shall calculate momentum by one particle, and in the second part we shall multiply the momentum by one particle into the number of particles and that are colliding with the piston per second, okay. So I'm solving the first part. In the first part we have to find momentum by change in momentum by one particle. So let's imagine that there is a particle that is moving with velocity v, that is moving with velocity v, and it has an x component vx, okay. It has an x component vx, and this vx hits the piston, okay. So and here let me say something. We are assuming that the piston is completely perfectly elastic, so that molecules that are colliding on the pistons are not losing their energy, they are colliding and getting back with the same speed. Okay, what is the flaw? If the piston was not perfectly elastic, the piston would heat up. With every collision, the molecules of the piston would gain some random motion, and the piston would heat up, and eventually when the equilibrium will be established, again the system will act like a perfectly elastic piston. So for sake of simplicity and for sake of general concern and considerations about the system, we are assuming the piston to be perfectly elastic. Okay, so let Vx, so the change in momentum, okay, would be 2mvx. Okay, let me write it more clear. So the change in momentum is mvx minus times of minus mvx. Okay, because after collision the molecules go back in the opposite direction. So, and this is 2mvx. Okay, now I'm calling this vx as the velocity by which molecules are moving. Okay, now that's the momentum change by one particle. Okay, so that's momentum change by one particle. Now how many particles are there that will hit this piston in 1 second? So let's say that there are n particles. For that, let's imagine that the volume of this container is v. Volume equals to v, and total particles are n. Okay, therefore number of particles in per unit volume are defined as n small, so I'm calling that number n, and that would be total number of particles upon the volume of the container. Okay, so this would be the n. Now how many particles will hit? So the particle that will fall in this region, let's say the particles are moving with vx. Okay, then only those particles will hit this piston in time t which are at a distance of vx into t. Okay, because जो particles इससे दूर होंगे, इस डिस्टेंस से दूर होंगे, लेट्स से यहाँ पे होंगे, वो टी टाइम में कुछ यहाँ तक ही पहुँच पाएंगे, वो पिस्टन को हिट नहीं कर पाएंगे. सो वही पार्टिकल्स पिस्टन को हिट कर पाएंगे जो कि टी टाइम में इतनी दूरी कवर कर पाएँ, और जो कि इतनी दूरी है. ओके, बिकॉज अगर पार्टिकल्स की स्पीड इससे कम हुई, तो अगर पार्टिकल्स इस रीजन से बाहर हुए तो वो टी टाइम बस इतनी दूरी ही कवर कर पाएंगे. ओके ओके, सो दिस विल बी the number of particles that will hit in time t. Now, and the total number of particles will be this distance, this is small volume. Okay, this is small volume. So in unit volume, we have this number of molecules. Then the total momentum change by all particles that will hit in time t is number of molecules in unit volume, that is n, and multiplied by this area, because the particles that are in this small area, that is vxt. So vxt into 2m vx. Okay, this is momentum by one particle, and this is number of particles into area. Now let me write it more accurate here. This is vxt. This is number of these are all the number of particles, and if you multiply it by area, we are covering this whole volume. So the molecules in this whole volume will hit the piston. Okay, so these are the number of all molecules that will hit. We are multiplying it by momentum of one molecule, so to get the net momentum change. Okay, so to get the net momentum change, that's the change in momentum. Therefore force would be this momentum change by time, the time it's taken, and that would be and this time would be will be cancelled. Okay, and let me just think again. Yes, force momentum force is dp by dt. Yes, so time would be cancelled, so this would be n m into vx square into a. Okay, this will be the force. I think I'm not missing anything. No, there is an extra 2 here, so let me write that. N into 2m Vx square into A. Okay, that's the force that the piston is that's the force by which the piston is getting bombarded per second. Okay, now we know this equation, that force equals to pressure into area. This is also area, this is, so we can see that pressure is actually nothing but this equation, N into 2m Vx square. Okay, this is the pressure, and we can see that pressure depends on the velocity by which molecules are colliding. Pressure also depends on the number of molecules that are in unit volume. Okay, I think that's the very idea of the pressure. Now we can see that there is a consideration that we didn't took serious while we were writing those equations initially, and the consideration was that every particle would have a different speed. Okay, every particle would have a different speed, but we imagined that every particle is moving at the same speed, so we have to correct that now. And how will you correct it? So we'll take average of square of velocities of all particle over the number of particles. So then the pressure would be written as N into 2m, and average, or you can say that the average of square of all particles taken. Okay, and this is how we represent the average. Okay, so it would be n times 2m into Vx square. Okay, now when we imagine that molecules in this volume will hit the piston, we thought that all molecules will hit the piston, but the fact is only half of the molecule, on a rough scale, only half of the molecules will be moving towards piston and half will be moving away from piston, because molecules are doing random motion. They don't know where to go, where to not. Therefore we have to divide this whole equation by a factor 2. Then we'll have equation n into m into this average of this is the average of square of velocities of molecules taken over number of particles. Okay, so this will be the equation of pressure. How? Let me again explain it. When we got this volume which will in which the particles will collide with the piston in time t, we thought that every particle will collide with the piston, but the fact is only half of them, on a rough scale, only half of them will collide, because half of them will be moving in different direction, that is opposite to the piston. So that's why we have to divide this factor by 2. Now there is another problem, and the problem is that we imagine that there is only velocities in the x direction, but the fact is the molecules will be moving in all 3 directions, and those 3 directions are in x, y, and z. So they will be moving in length and width and height with the same speed, on a rough idea. So we can say that this Vx square, this average of, so we can assume that this Vx square would be actually equals to the average. I'm sorry to use, but that's how we can imagine it. That would be average of these terms. That would be the average of these terms. Why? Simply because we assume that molecules are moving just in x direction, but the fact is they are not moving in x direction. They are moving in all possible direction, whatever they have. And interestingly, we have just 3 dimensions for a molecule to go, and that is that. Okay, now we have got a very beautiful equation. And what is that equation? The equation is that pressure equals to, and we'll substitute this value here. Okay, so how we can write it? And to make it more simple, let me think. Yes, I'm calling this velocity Vx square plus Vy square plus Vz square as I'm calling this velocities as V square, simple V square, velocity that molecules have, because these are actually, because Vx and Vy and Vz are actually components of the velocities. So I'm just imagining it the velocity V, because that's where it was given, velocity V. Okay, so this whole thing will be almost the 1/3 of V square. So we can write pressure equals to N into M into, and we can write Vx as 1 by 3 of V square. Okay, we can write it like this. Now what I'm going to do is I'm going to multiply it by I'm doing some manipulations to get a very familiar term. I'm sending this M into this bracket, and I will multiply it with by half. So let me make it that first. So this will be M into V square, and I'm dividing it by 2. Because I have divided it by 2, I have to multiply it here, and this is what we get. Okay, so that's the case, that's the pressure. Now we can see that this term is actually the kinetic energy, mv square by 2 half mv square. This is the kinetic energy of the center of this is the kinetic energy of the center of mass of molecules. So we can write that this is and this energy is for let's imagine if the gas in these molecules, if these gaseous molecules in this container are monoatomic, then all they will have is kinetic energy. Their all energies is constrained in their kinetic in the motion of their center of mass. And if there are two molecules like this, let's say two molecules of let's say CO, then these molecules will vibrate along this bond, and all energy they would have will be not just kinetic energy but also this vibrational energy. But we are not considering this here right now. We are talking about monoatomic gases. Okay, so while talking about monoatomic gases, we can assume that all energy the particles have are in the form of their kinetic energy of the center of mass. Okay, so we can write this pressure equals to 2 by 3 N into U. This is U, and this U is actually, let me write it more accurate, this is U, and this U is actually internal energy. Conventionally it said internal energy. I never got the sense why, because what's the meaning of, because when you are saying internal energy, what is external energy? But that's not our concern to think. Okay, so that's the pressure. Now we have this equation of N equals to number of molecules upon the volume. We can use this equation here. So what I'm going to do is I'm going to multiply this equation with V. Okay, so let's see what we get. I'm going to multiply V both sides. Let me just divide this segment. Yes, I'm going to divide it by I'm going to multiply volume into LHS and RHS. So what we'll get is we'll get PV, and we'll get 2 by 3, and if we'll multiply this NY, that is N is actually number so we'll get N into U. Okay, that's what the equation will get. Okay, now what this equation says, this equation says that you can relate, for example, if you have a container with a gas, so you can relate that if you will compress the gas, how much energy will change. So, or you can say that for a how to put it in words, yeah, so I mean you can relate that if you are given a gas, okay, and you are told to compress it, how much energy would be required to compress the gas completely, or to compress the volume by certain extent. Okay, so this all sorts of question could be asked. And then the problem is that when you will compress this piston, where will all the energy go? Okay, now if the walls of this container are, let's say, we call adiabatic, if the walls of this container are adiabatic, then all the energy will be converted into the energy of molecules, because in adiabatic conditions there is no heat leak, no heat will leak through the system. But if this is not adiabatic, what will happen is when you compress the piston, the molecules will gain random motion, and those molecules will hit the walls of this piston, the walls of this container, and they will heat up. They will shake the particles of the walls, and certainly the wall will heat up and will lose energy. Okay, so for simplicity, for a general case, we are assuming that these walls have no energy heat leaks, which means that these walls are not getting heat up, and Thus this is an adiabatic process, which means that energy is not is escaping the system. That's what we call adiabatic system. So in adiabatic condition, all the energy that we need to compress, all the work we have done to compress the piston will be transferred into internal energy of the change in internal energy of the system. Okay, so we can say that change of internal energy, that would be how to put it again, but let us talk here. First let me talk about this. So if this is monoatomic, then this holds true. But let's say if the gaseous molecule is diatomic, then all the energy will be not constrained in the kinetic energy. Some energy will be the energy of the vibrations of molecules. As I told in the example of CO, there are two molecules. The C will vibrate in its own position and O will vibrate in its own position along the bond length. Okay, so so for a general convention, we can write this term as in generally gamma minus 1 into n into u. Okay, we write that. So that's how we can think it. So that's the condition, and this u was kinetic energy of one particle. So total number of particles into kinetic energy, this will be kinetic energy of system. So I'm just writing it here. I'm just taking this n now because this this is internal energy of one particle. Okay, and a number of molecules into internal energy of one particle. Say this is internal energy of system. This u is, I'm calling this so okay, so this u is internal energy of all particles, that is internal energy of system. Okay, that's how it is defined. So let me fix the camera again. Yes, so that's how it is defined. So we can see, and we know that in adiabatic compression, all the energy goes into internal energy. So from that we can write an equation that du would be pdv, that is work done, or we can say that just let me think again. Yes, so pv equals to v. Finally we got the equation that pv equals to gamma minus 1, okay, into u. That's the equation. Gamma minus 1 is just a constant for a monoatomic gas. Gamma for a monoatomic gas, gamma equals to 5/3. So 5/3 minus 1 is 2/3. Okay, so we can have all such values of gamma depending upon the structure of gas. So that's the condition. We can write u as pv upon gamma minus 1. Okay, so and du would be 1 upon gamma minus 1. pdv will I am partially differentiating this, and this is vdp. Okay, this gamma minus 1 will get multiplied here. Is a simple mathematical operation that's called cross multiplication. So this will be gamma into du minus okay, and we can write du also as, what is du? We can write du as work done. Okay, because we know that in adiabatic compression all the work done is transferred into internal energy. So this du is actually the work done, and work done is what? Pdv. Okay, so pdv equals to 1 upon gamma minus 1 and this pdv plus vdp. Okay, that's the thing. And we can multiply this gamma minus 1 here, so we'll get gamma into pdv minus of pdv equals to pdv plus vdp. Okay, that's the equation. Now all we have to think is, I must have done some mistake. Sorry, work done is minus pdv. Okay, internal energy is actually the work done in adiabatic condition, and it would be minus pdv. So this would be minus, this would be plus. Okay, so this pdv is cancelled here. Okay, and we can say that this PdV, this gamma PdV is actually equals to minus VdP. Okay, so what I'm gonna do is I'm gonna take this V here, and I'm gonna take this V here and send this P here, so that to form a familiar differential equation. So this would be gamma into dV by V equals to minus of dP equals to minus of dP upon P. Okay, let me think whether it's perfectly accurate or not. Yes, I think this is accurate, and what I'm going to do is I'm going to integrate with both sides. So by integrating, what we will get gamma into ln V equals to minus times ln P plus of ln C. Okay, I'll take this equation here, so we'll get gamma into ln PV, because log addition of two logs with same base multiply, so ln PV equals to ln C. And in log we know that this constant can jump over PV, so we can write that PV power gamma equals to C. So that's a very familiar equation we derived, and that's the equation which I wanted to derive. So for that we have to begin from the very basic, the momentum of one particle. What we did was to multiply it with the number of particles. We found the number of particles in a unit volume, then we find the number of molecules in a unit volume. We multiplied those two factors. We had some assumptions, then we later corrected it. We later assumed something else, then we also later corrected it, and finally we achieved this equation. So this is the most important equation in adiabatic expansion and compression, which is PV to the power gamma is constant, and this gamma is again the same gamma which we shall use here. So for example, for monoatomic, this gamma would be 5/3. Okay, and this constant is this is constant. Okay, so we can say that for any adiabatic process, expansion or compression, the kind of the relation of pressure and volume has a certain constants, has a certain relation that is determined by this factor gamma and is constant. So and the term PV raised to the power gamma is constant. That's all for today, and that's a very general talk about adiabatic process, which Richard Feynman has explained in his book Feynman's Lecture on Physics. That's all for today, and I shall take a lot of these processes and a lot of these interesting illustrative thoughts that are embedded in some very interesting books. So that's all for today. Like, share and subscribe. Thank you.